phase. 3, 2, 1, done. I'm gonna just tonight. This is on video is on quasi-systems. But you know, these are really the systems that resolve Eulaearn Hamiltonian systems for quantum or quasi-states. But you know, we got the Kleene-Goldberg rule for quantum mathematics. But you know, the Kleene-Goldberg thing, I don't really understand. Understand it's like a wildcard state. So you have some kind of sigma notation or language that you know, basically the Kleene-star from language theory, automatic theory. It's not the same thing I'm using for the Kleine because that's familiar enough. I'm putting it together. So but basically I'm trying to state formalize the Kleene-star as the Kleene-star, you know, which is like the wild card, which matches basically is for Rift, but for quantum states, for quasi states, it's the same thing as the Kleene-star, the Kleine-Goldberg equation, but it maps topological, it's topographic, because I know it's the same, because there's several problems you can solve with it. But I'm gonna get tired now, so we just get started with it. So, why this model? So the Kleene-star is really used for wildcard matching. So you got like some kind of summation of sigma star that lies on the set of languages that you're enumerating over the alphabet layout. The same thing applies for the Kleene-Goldberg rule, because the Goldberg rule works in Hamiltonian enumeration. You can use this to structure data. Oh, I'm actually gonna type. Oh, you can use this to structure some information. To compute over Hamiltonian state, Hamiltonian and Eulaearn functions without anything behavior, because it works as intended, because you are just enumerating, which is the key. You are enumerating systems of different properties. But you know, the Kleene-star, it's really just works best on classical system. But for the Kleine-Goldberg equation, which I'm going to show the same right again. Sorry for a place like that. Is another Kleene-star for quasi-systems. Now, what is quasi? Quantum systems are quasi if they have topological states, topological and tomographic states that they have to resolve. For example, if you have a consistent system, let's agree to disagree. If I say yes, you say no. We have permission to agree. But if you say yes first, and no first, and I say no next, then I know your no, yes is no, but we agreed then, but we don't have the right to agree. So that's the first one. So if I say no, if we shuffle this over the rule, we get like a yes, I know, and then I say, then we have some misunderstanding. So you have a 1, I have a 0. I have a 1, and then you have a 0. Because you know, then some kind of switch. Because you try to match my no equals my yes, but you know, there's no implicit rule or to drive this equation, which is what the Kleene stuff is doing. For example, if I say 1, you say 0, and I say 0, you say 1. You know, I say 1, you say 1, and I say 1, you say 0. You know, these 4 states is quasi-state, but we're trying to create some kind of functor that isomorphically resolves the state via consent, level consensus. Because if you say 1, if we have 2 1s, we share one state, one equilibrium, there's some kind of arbitrary state, like you know, some states that the function is in. For example, 1 yes, my yes is your no. Yes, and your no, or if you say no first, it's my yes. So, but it's my yes. But you know, this is a state that we have to resolve non-deterministically. So we can group this in pairs, in tuples. For example, 1 1. This is no's. These are no's. We cross them out because that's what we need. We can use them to Strauss. But what we need is 1, my first yes, and your first no, and your first yes, and my first no, and your first yes. Both ways. That's the idea there. So you know, we have this kind of Kleene-star that gives you the topographic data. What do I mean by that? So the kind of topomology I'm talking about is the, you know, the area. What does this mean? Basically, we're trying to listen for the resonance of the system. what is the best canonical representation of the state. You know, it doesn't matter the bits that come into play with this. But I'll give you a problem. So the problem now, because the system has to be clear enough to process, store the information to keep the information coherent for the system. So if so we have to get another encoding layer. So we get 0, 1, or 0, 1. So we share 2 bits. We only share a state space. We say initially, I have 2 bits of memory, you have 2 bits, but we only allow 0 and 1. You know, 0 and 1 at a time. So that means they can be 0 and 1 can be instead of 1 1. We only let upper 1 or 0. So at the time, so you have to do some context switching. So how does it work? Firstly, if you say 0 0, you have your private 0, or you know, you have a 0. One that's changed, you can change. I don't think you can flip it. So if I say 0 and you say 1, if I say 0, we disagree. You know, but then if I say first, you know, I can trigger keep my 1 private, and then you can say yes, this is a no. I mean no, you mean yes, but I say okay. Then I said that was the first trial. Now the first trial consists now. If you want to flip your bit, your epsilon bit, you turn this epsilon bit on. So you say this is yes. You send me the no. You send me your bit. So this is your 1. So you give me another bit. This is epsilon. So this is like your epsilon. So I get your epsilon. Basically, because I send it to you, you get my epsilon, and I take my epsilon, your epsilon, and look at my epsilon. This is nothing. This is nil. This doesn't mean anything. So I then get another bit, and I get another bit. So and I'll flip this to your epsilon 0. Now this 0 is your no. Your no. I mean your no, but it's my yes. My yes. So I send this in the next operation. So this becomes from this 1, I've changed to 0. So that's all I've done, and that's what basically my friend had done. So I'm now receiving a 0 as a protocol, but I know 0 it means yes, 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 yes. So I say oh yes, it's yes. So and I say yes. So basically yes, and I check it, and this is yes. So it only works on permission and consent. It doesn't need to use consensus in English before, because you know on the classical system you need consensus. The extra bit was already classical, 2 bits for by 2 because you know, the system already knows that you only need state. You know, if I want to send you, if you want to, if I start a communication and I'm sending you, I'm sending you 1, and you know to no, you know you can accept it. You have to check whether you can it in your encoding table before you can do it for your communication. Which is what the goal is here. So we can continue communication here because you really decipher that message, what that message means, because you got the encoding table loaded in memory. So when you see that kind of information stream 1, you see in my 1, you know it means a 0. It's no 0. If you see on my 1, it means it's your yes, which is a 0. 0. If I see your 0, I know it's my yes, based on epsilon state encoding. So the real power of this quasi-state is not because of the concealed body, it's more about the Hamiltonization cycle over epsilon transition. For example, you can define a quasi-state via the ontological. The quasi-state is like the parity bit, you know, parity elimination encoding. So it's like a parity encoding. So it's like I call it parity elimination, but it's like a, you know, if I get if you say yes, I mean if you say yes, that's my no. That's a 0 to me. So if I say no, if you say no, if you say no, that's my yes. So yes, 0. If you send in 0, I know it's my yes. So that's it. So parity coding is that kind of thing you do to ensure the system doesn't falter or go off way, because it's very important to parity eliminate the kind of some kind of piecewise function that maps over the states of epsilon. Because you know, for example, my we have 2 encoding states, epsilon and negative epsilon. You know, these 2, we can have epsilon before negative epsilon, you know, in that order, in the reverse order. So you know, so no matter how you model like a vector, you know, the goal is to have some kind of lattice bound operation that share the consent space for for coherent communication as a bridge via superposition as the protocol. So basically, the conjugate lattice of this is like, if I have one e minus e, then an e, I have the opposite of 1 over minus e to e. Have the conjugate. This will be the other one polarized. So where I'm going with this is it's kind of sounds silly now, but say basically we're in Rubel. Basically, photon is like a propagates wave towards the what you seen. It propagates wave up and down, like a forward. But for you to get this meaning on this photon in some kind of alternate reality, you have to reverse it via. So if you're using Hamiltonian neutrality, using Eulaearn, your Eulaearn model in the other universe. So you have to, the better way to do it, you have to like sync it with your Eulaearn edge-bound system to get information. Get what I'm seeing. Because it's so far away, it's like a redshift. So basically, I have to like take the redshift from your universe and reverse it to blue shift. So I can get some sense of it, or full sense of it. So that can be done quickly. But especially in some other universes, you get instead of redshift, you get blue shift, because that's our universe is blue shift from your universe, because it goes like so far. Your blue is my red. That's what I'm saying. So the idea is to ensure the photons are sent, without being tampered with. Because the photon is the photon, matter the property, how you model it, sparse or not. So the idea here again, so you get the model there. So for example, let me give you one problem. So let me try to give you a problem. So say I sleep. I'm going to sleep now. So I'm getting sleep soon. 8 hours I sleep. From anti-clockwise rotation, we get the polar corner system. So if I sleep half an hour, I get 90 degrees, which is your universe minus 90 degrees. So because we have an anti-clockwise system. My universe 90 degrees is your universe minus 90 degrees. Because minus 80 degrees, 180 degrees. So is your counter 180 degrees minus 180 degrees. And if you imagine my universe 270 degrees is your universe minus 270 because it's counterclockwise. Basically my counterclockwise universe works differently here. So it's like counterclockwise, but it's synced. So we can't sync, because we have work on different roles. Like the Eulaearn cycle, you have my Hamiltonian cycle in my universe, because they're the same thing, but working for different purposes, different ways thing. So if you go, if you have basically this is like a 360 diagram, where the modulo is a 3. So basically, if I go counterclockwise, I can go clockwise as well. Your universe, I can measure universe from my universe, full observation of your universe and my universe, but I have to do some thing, because your universe is like a kind of a relative. So after taking the account of the quasi-state or relative, because quasi-states are dual states, and dual data. They work on the data being parity, having two kind of sort of parity of piece function, which is like when you model the system cycle state, because they work on like Franken functions. If you don't know what they are, like what is this? You get an input if x is less than union, if x union, if a and b, if x and union y. Some kind of I'll go much earlier. But listen. So the idea is when I sleep, well, if I sleep 8 hours, that means 24 hours in my day, and you're there. 24 hours in my day, and you're there. But if I sleep 1 hour, 24 hours, that means there are no 24 hours in your day. That would be 90 degrees, minus degrees into 90 degrees. That would be half a spin of a sleep state. Now I'm allowed to sleep. Basically, we get 16 hours. My 16 hours equals your negative 16 hours. So I'm trying to sleep 16 hours. So for me to sleep 16 hours, I have to go half a day, another day, which is like over 8 hours. A day is my framework what 8 hours. So this is basically over half a day is like 6 hours is half a day. A day is 8 hours in my day because 8 o'clock, 8 a.m. So you wake up 8 a.m. So you get in the net 8 p.m. or 8 a.m. p.m. AM p.m. first. No. So I get to now. I'm currently at a state of 2 1. So you get half pi, and then you get pi, which is like which you get pi. You get a sequence of nil or pi, nil pi, and then you get a half, a quarter, pi. Then you get look at you get a quarter, a pi. Pi is the radius. No, because you get nil. You get nil. Then you get pi, because it's the radius then of the system. The full magnitude. You get nil, and you get 2 pi. Is it 2 pi? And you get 4 pi. 2 plus 2. So you get half, 2 and a half pi. 2 plus half pi. You get 2 and you get pi. You get 3 pi. You get 3 pi. If you are at 270 degrees angle, 3 pi is and you get 4 pi. That's the full maximum. So you get increment of pi. But pi is a spin. So if I spin the sleep cycle, if I basically 16 hours awake, I'm sleeping hours sleep. But I store some data. Say I want to remember some fact to upload this video at exactly some time in that framework. So I'm trying to give you a communication. I'm really tired now, but I'm giving an example. So I'm just trying to not fall asleep basically. So 16 hours is my cycle. So I'm allowed some kind of rest. So I'm not thinking about the work. Basically, if I remember that I have to wake up in 2 hours before I start my day. 2 hours before my day. That will be 8 a.m. So the 8 a.m. But 8 a.m. I wake up. Into 2 hours. 8 a.m. I wake up, but 8 minus 2. So I get 6. So 6 a.m. I should wake up. Definitely 6 a.m. So only that's 6 a.m. But the computer has to do this in parallel. So what would I do? So what would my sleep state do? So I put this data in memory. I take this state of 6 a.m. To just wake up. But I'm half asleep. Basically when I start my eyes and go to sleep, into the sleep state, sleep like I said, I half asleep and half awake. That's the goal. But this is basically when the process run, because it's not I am dead. It's because I'm half awake. So if I'm half awake, I'm half asleep. If I'm so basically this operator could quasi-systems run in parallel. So I have I can do my process of half awake here. Anytime my cycle or spin does, so I can polarize myself to the goal of waking up at 6 a.m. Like a good body rest. So for example, if I'm half awake, if I'm half asleep, that'll be 2 pi, because I get 0 pi, and then get pi, and then you get pi, and you get 2 pi. So that's the maximum allowed to sleep. 2 pi spin. So the quantum system will have to allow me to go 2 pi sleep, maximum sleep 2 pi. So if I take 4 pi, I've existed the system. Because 4 pi, so obviously if I want to sleep well, I have to have 2 pi. But if I want to sleep, I have to start waking up from 2 pi to 1 more pi, from 1 more pi rotation to 3 pi. I get the spin definitely wake up to so I can get that 6 a.m. deadline, which is 2 hours on the dot before 8 a.m. Because I don't have to think about it if I set the reminder. So before this, which is the quantum system has to polarize the quantum states and ensure there's no because nothing to you have to agree on the consent system. So the quantum system state must represent the kind of data model, because if I sleep 3 months, I will, but I pass up. If I'm half asleep, if I'm half awake, my body. If I'm half awake, my body. If I'm half asleep, if my body is half asleep, then my mind is half awake. They channel the system to which is cool, because the system doesn't need to maintain any more data because it's really a state, entangled to that superposition, which is the quantum abelian of Hamiltonian Eulaearn graph-based edge-bound resolution Hamiltonian cycles, which are like depth first search and breadth first search, because that's the idea. So basically, sleep state is kind of like a pseudo. It's not a pseudo state. It's not a pseudo state. It's like half true. If some data unit is half true, it's half lie. if some information is half true, tomographically it's half a lie because it doesn't give you the full information. Because tomographically, you have the 2 pi, and 2 pi can be you get pi, which is like the radius, and you get 2 pi. That's 2 pi, which is half 1 awake. Yeah, but that 1 awake is considered 1 pi. So if I if I'm awake, I should have already completed the pi, which is sleep. But sleep is not good enough. So I get the sleep paralysis and then get the pi. And if I want to do it away, but I can do it at the same time because it's 2 pi. So the kind of thing it's about morphy is about measuring the area on the curve. So if this is pi, I can use the standard Hamiltonian model for the scenario universe as a depth first algorithm for the data set 6 a.m. So 16 hours, 6 a.m. I wake up. That would be. I haven't got enough paper, guys. Let me try this over for you. So I'm trying to give you my example because I don't want to fail you guys now. So the one I do is like 16 hours 24 minus 6 is 24 minus 16 is 6 hours. Now this 6 hours is the maximum allowed to basically 6 hours 6 a.m. I wake up. So I can do 24 minus 8 I get 16. I get 16 hours but I wake up 8 a.m. So this 16 hours is a.m. and p.m. Shared time, but this time was in cycles. So if I divide 16 divided by 2 cycles, I get 8 hours per day and night. 8 hours maximum. But if I divide 6 and 2, I get a shared space of 8 hours, a.m. and p.m. Shared space. So I need a maximum of 4 hours sleep per a.m. A week, and for p.m. 4 hours for time.